Hi, I'm Jazlyn, since no one introduces you. I am currently at USC in their Department of Quantitative and Computational Biology. I started there in January, so the lab is very new. But I was fortunate enough to see a lot of your great faces here at UCLA when I was doing my PhD with Kirk, who also left me hanging today. Apparently he's on vacation, but I'll make sure he watches this. So today I'm going to talk to you about my postdoc project that I did at Stanford with a different Noah that's here. I was in Noah Rosenberg's lab, so there's two Noahs, but it's on the number of genealogical ancestors and how many of them we can trace back to source populations if we're thinking about an admixed group. So the talk is split into two parts. I'll give you a section of background that's pretty heavy on the US history, just because I think a lot of the material is very relevant and not often covered in classes. So most of it you have to seek out if you really want it. And then in the second part, I'll talk about using this discrete model of admixture and autosomal information to compute the number of genealogical ancestors. So, I'm going to be talking about a period of US history that's spanning slavery. This is a topic that's very important. It's close to my family because I am African American, and it's something that's not often covered in classes as in depth as it should be. So I'm going to roughly walk you through this very simplified timeline in the next 15-ish minutes. I'll dive more deeply into it. But just to start, many of you maybe heard about the 1619 project. So 1619 actually marks the beginning of what's known as chattel slavery in the United States. And then we see that the importation of slaves is basically becomes illegal in 1808. But then there's a period of time between making the importation of slaves illegal and the actual abolishment of slavery. So the abolishment of slavery is not until 1865. And actually during that time period between 1808 and 1865, the last slave ship that we know of landed in the US in Mobile, Alabama. It's a ship called the Clotilda. That was in 1860. So actually one of the last people who was transported to the US on the Clotilda, she did not die until 1940. So this is a very recent time period. And then after we have the abolishment of slavery, we move into this era that, depending on where you're from, so it's known as segregation, the Jim Crow era when you're thinking about the South, and that ends roughly in 1968 with the Civil Rights Act passing. So to start with, I'm going to highlight this beginning portion of slavery in the US. So let's hope this works. So what I'm showing here is a graphic of slave ships that are moving from Africa into the Americas. And what you'll see is that it starts actually rather far before 1619. So it actually starts in the 1500s. And so during the period of the 1500s, what was not happening was chattel slavery. It was actually indentured servitude. So basically what this means is that race was not factored into slavery. So individuals who are African, individuals who are European, they were in indentured servitude where they would work. And then afterwards, they were either they paid off a debt, or they were set free. And it's not until the 1600s that we get the introduction of chattel slavery in the Americas. And now what you'll start to see is that more and more dots are flying across. So the transatlantic slave trade starts to peak in the 1700s. So that's when we're going to see many more ships transporting individuals from Africa into the Americas. But what you'll notice also on this map is that not a lot of these ships are actually moving into the United States. The vast majority of the ships are actually moving into Brazil and the Caribbean. And so what ends up happening is that even though roughly, depending on who you're talking to, 12 to 14 million individuals were transported as slaves into the Americas, only roughly 500,000 of those individuals actually were moving to the United States. And of those 500,000, we know that roughly 10 to 15% did not survive the Middle Passage. So that's pretty ugly when you're thinking about it. And what I also want to note is that the reason that the United States slave trade was able to persist this way is because of how it operated. So in Brazil, many of these individuals worked on sugarcane farms, and oftentimes what would happen was they would die before they reproduced. So the lifespan of a slave on these farms was very short. However, in the United States, what ended up happening is that even though conditions were horrific, right, individuals were able to reproduce and have children. So what ends up happening is in each state, we had what were known as slave codes, which were codified into law. And these slave codes are basically what allowed the amount of slaves in the United States to increase quite rapidly. So individuals were able to have children, but slavery now became something that was inherited. So if your mother was a slave and you were born to her, you were a slave too. Slaves were considered property, right? So they could not own property. You could not teach slaves to read. So this is all what's happening in these laws, these slave codes that were codified. So this is just another set of numbers so that you can actually see how many individuals were actually sent across the Atlantic Ocean and how many people actually made it across. So of the 31,000 ships that were shown in the previous slide, there were roughly 12 to 14 million individuals on them, and roughly 89% went into Brazil and actually not into the United States. So we've gotten past this point of slavery in this in the time lapse that was shown. So now we're at 1865, and then after 1865, we get this period of time that's segregation and the Jim Crow era. And during that time, there were a lot of landmark civil rights cases. I've only shown 2 here, but we see Brown v. Board of Education, where we see schools start to get integrated. Busing is happening. There's also in 1967, Loving v. Virginia, where interracial marriage is allowed. And then finally, in 1968, we get the Civil Rights Act being passed, and this was championed by Kennedy. When Kennedy was assassinated, Lyndon B. Johnson was like, let's pay homage to Kennedy and push this through. So this brings me to my project, which is on tracing genealogical ancestors. So this topic is very important in US history, but there are also a lot of people who've been looking at it from different perspectives. So I really encourage you to look at this Nat Geo issue. And if you can't, Into the Depths is also a podcast. It's available on Spotify. And it's about a woman who actually goes and gets trained in scuba diving and then begins looking for shipwrecks of slave ships. And then there's also In Search of Our Roots, which is written by Henry Louis Gates, but he has a TV show that goes along with it. So in this book, he talks about 19 extraordinary African Americans and their families' genealogies and how he's able to trace them. And the extraordinary part is, they're extraordinary humans, but they're also famous. So they're people that you might know. So the one who really stood out to me was Quincy Jones, because I love music. So it turns out that for Quincy Jones, he was able to trace his European ancestors all the way back to the monarchy because they were cousins of the monarchy who then moved into the Americas as another way to make money. The other person who he talks about, and I think that really stuck out for him, was Don Cheadle. So if you've seen Hotel Rwanda, Don Cheadle is one of the big actors in there. And in this case, there's a different type of slavery to think about. So Don Cheadle's ancestors were actually owned by Native Americans. So not a lot of people talk about that there was even slavery within the US and in Native Americans. So they were actually chattel that went with them on the long walk. So there were slaves that went on the long walk, which is, that was the first time I had ever heard about something like this. So those are 2 stories that stuck out to me, but there's a bunch of other great stories in there, and there's actually a book entirely about Michelle Obama's history. It's called American Tapestry, if you're interested in that, it's something that you should definitely read. So the last part I want to end with is, why can't we trace our genealogies? And the answer is because the first census that actually contains data about African American individuals isn't until 1870. So prior to 1870, there's roughly no information about your relatives unless they were sold, or there's some records of births in some plantations. So the information is very limited. So our goal here is saying, we have historical information. How can we use what we know about mathematical modeling and history to gain more insight about the past of America? So one thing that I want to clarify before I go any further is there is a difference between your genealogical ancestors and your genetic ancestors. So I think if you haven't ever looked at Graham Coop's stuff, go look at it. It's great. He gives great explanations of things. But here I've stolen these from Graham Coop, and what he's modeling on the graph on the left with this red line is your genealogical ancestors. And we know that those basically are doubling for every generation that you're moving back. And what you see with your genetic ancestors is after roughly 10 generations, they start to really pull off from your genealogical ancestors. And this is just because of recombination, right? So there's not enough room on your genome to have basically memory of all these ancestors. So another way to think about it is with this graphic here. So you are the individual who's the white. You have right chromosomes from your maternal and paternal side. So that's either side here. You go one generation back, you're at your grandparents, you're at your great-grandparents, your great-great-grandparents. And then what this blue line or blue arrow here is pointing to is white space. So that's an ancestor who is your genealogical ancestor, but not your genetic ancestor. So as you can see, the further back you move in generations, we see more and more white space cropping up. So, like I was saying, how do we get from what we know and some genealogical information all the way back to the past? So this is actually my family's genealogy. My grandpa's really into genealogy, so he spent a lot of time in libraries collecting this information, and he's able to do really well for my mother's side of the family, because it turns out we trace most of our ancestry back to Spain, and we were basically booted out with all the other Jewish people. So it goes quite far back. And this is one example of a relative that he found who's recorded in a census in New Mexico. And his name is Luis Pineda, and he's marked in this information as the color quebrado, meaning he's admixed. So that's just a word that was used often in Santa Fe. So there's some information about him and his family here. So this is my mom's side of the family tree, but for my dad's side of the family, we have roughly no information other than stories that are told and passed down. So just because the audience is wide, very basic kind of information coming next. So what is an admixed population? Just to remind you. So an admixed population is just a combination of multiple sources. So you can imagine one individual from an admixed population, their genome is just a random outcome of the admixture process. So if we were to zoom in on individual chromosomes, what you might see is one generation after admixture, something like this. Like we have full tracts of ancestry from both source populations. But in reality, we're looking at a person who's in the present. There's often been many generations since admixture. Admixture contributions can vary, and we get this chromosome that's a mixture of ancestry segments from multiple populations. So the actual information that we're going to use in our model isn't even local ancestry, it's global ancestry fractions. So we're saying something like, we sample individuals, we see that they're 70% red, 30% blue. So that's all the information that we need for our model. So very classically, admixture has been modeled with much simpler scenarios. So here's just two random examples that I pulled. So the swordtail fish and butterflies. So these two models, there's a hybrid isolation model and the continuous gene flow model. With hybrid isolation, what happens is you have this pulse of ancestry from both populations. then there's no gene flow afterwards. With continuous gene flow, we see this pulse of ancestry, the admixed or hybrid population is established, and then we see one-sided gene flow. And generally the rate will be the same across generations. And then you would just do the same thing for population 2. Now, what makes our model unique is that it's much more flexible. So we're using this discrete model per generation of admixture. So let's just label our source population. So we have S1, we have S2, that's our blue population, and then our admixed population, we're going to call that H. So if we have this model of admixture, what we can do is repeat the admixture process forward in time, all the way until the present, and at the final generation, we can estimate the contribution of ancestry from each source population to the hybrid population. So what comes out is a distribution that looks something like this. And this is work that was previously done in Noah's lab with, actually Jay, he has a great project that's close to this, but looking at the traits, and Amy Goldberg and Paul Verdu did a lot of the foundation on this. So what we're interested in is saying, if we have an admixed individual in the present, how much ancestry is coming from either source population? So the reason that we're actually able to compute this distribution is because we can enumerate all possible parental pairings. And so I'll walk you through how we do that. So this is just right at the top of the diagram that we had before. So in generation 0, our admixed population isn't established yet. So your ancestry is coming from either source. But after generation 0, once the population is initialized, we now have 3 possible sources of parents. We have our S1 population, our admixed population, and our S2. And what the little s1 and little s2 are parameterizing is the contribution of ancestry, or you can think of it as the rate of admixture from a given population. So let's just say I sample an individual from the admixed population and I wanted to know, okay, what is the probability that both parents are coming from S1? Well, that's just the rate of admixture squared. And if I was asking, what's the probability that parents are coming from S1 and H? Well, then that's just the rate of admixture from S1, and then we take a random sample of individuals, of one individual from the admixed population. And the reason here that it's multiplied by 2 is because I don't care whether your mom or dad is coming from the population. So you can collapse those into one probability. And then we can just go through and fill in the remainder of the table. So now we've enumerated all possible parental pairings and what the likelihood of us seeing them is. So then it just kind of comes naturally. The offspring's ancestry is here just going to be the average of the 2 parents. So we can use a nice recursion equation and we can get this distribution of mean ancestry. And so I just want to say for the present, if we're looking at our admixed population, this alpha value is just denoting the autosomal ancestry fraction from either population. So alpha can either be 1 for S1 or 2 for S2. And that's in an individual from population H in generation G. So that's close to what we want, but not exactly what we want. What we want to know is how many ancestors do you have? So we're going to denote this with the random variable z. So the number of ancestors from each population, what exactly is that? In other words, I'm saying, given I see these chromosomes, can I tell you that, I don't know, 2 of your ancestors are from S1 and 1 of your ancestors is from S2. So that's our goal. How are we going to compute that? It's actually really nice and really easy. So just think of it in an intuitive way. So this is one time where your intuition actually works out quite well for you. So now I'm asking you, right, given I see this parental pair, S1, S1, how many of the parents are coming from S1? 2. So if I see the parental pair S1, S2, how many parents are coming from S1? It's just 1. So now what you're doing is you're actually summing lineages rather than using multiplication, and you can just fill in the rest of the table. So if we have parents that are coming from the admixed population, we just sample that admixed population twice. So we just repeat this process for source population 2, and now we can have the number of genealogical ancestors from source 1 and source 2. So the distribution, so this is just a random population I simulated, might look something like this for expected number of ancestors. And you'll also notice, right, that the difference is roughly a factor of 2, which can be horrifying in PopGen, but here is actually really nice since we're summing lineages. So now we have our full model, and we can now ask our question. So what can we learn about African American population history just using global ancestry information? So like I said before, I didn't want to give you useless information in any way, shape, or form. This information is very relevant not only for US history and just us to know in general, but also for our model. So here I'm showing a diagram of our model, and we basically are simulating population history that's split into periods or epochs. So there's 3 epochs, and epoch 1 is encapsulating right early slavery in 1619 all the way through the time when the importation of slaves became illegal. So this is 1808. And then the second period is encapsulating 1808 to 1865. So this is when slavery becomes illegal. And then our last period is going from 1865 until the present. So it's ending in 1965. And the reason is because most of the data that we actually have from African American cohorts, these individuals were born in and around 1965. So what we're going to do is we've generated this demographically informed parameter space, and now we just want to identify the sets of parameters that satisfy our model, and it's based on autosomal information. So just to walk through exactly what the model parameters are, in epoch 0, we have all of your ancestors coming in from Africa. And that's because, right, the slave ships are coming in. There are no African Americans at this time. There's only Africans who are being transported to America. So there's no contribution of ancestry from either H, which is African Americans, or S2, which is Europeans. So we're going to have a parameter trio for each generation and each epoch. So we have S1, H, and S2. They must all sum to 1. So that means you have 2 parameters that are free, right? And then if you take 1 minus the sum of the other 2, that's going to give you your third parameter in the trio. So here's where we now start to incorporate more demographic information. So we're going to introduce this new variable, CG, in epoch 1. And what CG is it's the fraction of non-European parents who are African arrivals into the United States. And we're able to pull this information from a combination of birth rates and information about how many individuals were actually being brought into the Americas. So we're able to partition those non-Europeans into Africans who are being imported and African Americans who are being born. So the official definition of African American in our model is just that you were born in America. So that's something that's also important to denote, is what exactly do you mean by African American? It's just you're born in America here. So in epoch 2, what we do is we just allow these parameters to range in value for what we think is reasonable based on the decline of the transatlantic slave trade and the increasing population of African American individuals who are already here. And we do the exact same thing for epoch 3. So we're gonna basically make a huge grid of possible parameters, and we're gonna search that grid. And so when we do, and we compute your expected number of ancestors, we see a distribution that looks like this. So this is the full grid. We're not using anything other than the parameter space that we've created. So now what we want to do, right, is actually say what information do we have and what can we use to thin down our results to a set of permissible values. And so what we use is just the autosomal ancestry fractions that have been computed from previous data sets. So we know across most data sets that the African autosomal ancestry ranges somewhere between 75 and 85%, and then there's some standard deviation of this ancestry. So if we incorporate those criteria, we can narrow down to our actual result for the expected number of ancestors. And that result is that if you are to take a random African American individual, you would see that on average, they have 51 European ancestors and 314 African ancestors. So in other words, we're on the level of hundreds of African ancestors and tens of European ancestors. And when you're thinking about what exactly does this mean in a historical context, right? What I'm saying is that maybe we're giving you some bound of the number of individuals who have survived the Middle Passage. And then as far as European ancestry, right, these, we don't know if we're not timing it, when it happens, but these are what we're calling European admixture events. So what we find also is that if we look at our model, as we add more and more African ancestors, we see a decreasing number of European ancestors. And this makes sense, right? Because there's a limited number of space on a pedigree. So if you're filling more and more of it with Africans, you have less and less space for those European ancestors. So we roughly see that there's this trend where there's a negative correlation. But the other interesting thing, right, is everything I've given you is just this bulk kind of, here's the number. We have this discrete model, so we can model this per generation. So here what I've done is partition the first epoch of our model into per generation ancestry contributions. And what you'll see is that at the beginning, if you're looking at an African American individual, most of your African ancestry is happening in that initial generation. And then this is, right, moving through the transatlantic slave trade. So as less and less slaves are coming in, we see less and less African ancestry, but more African American individuals are being born, so we see this corresponding increase in the number of individuals who can trace their parents to an African American origin. And then in Epoch 1, we fix that European value, so we see that roughly 8% of ancestry is coming from European parents. And if we look at Epoch 2, where we no longer had that CG parameter, so we fix everything across all the generations included here, we see that most of the parents are African American. And the same thing holds for Epoch 3. So this is getting into the present day. Most of your ancestry is coming from African American individuals, but there's still some small bit of European ancestry as well. So one of the last things that I want to talk about is what happens if we partition per generation for our expected number of ancestors. So we can do this by just looking at a non-recursive mean. So on the x-axis here is each generation of our model. On the y-axis is the number of ancestors that are coming in at that generation. And we see that there's these peaks in generation 4 and 5 for both African and European ancestors. And so these peaks roughly correspond to the height of the transatlantic slave trade. And this makes sense. So most of your African and European ancestors can be traced back to that period when slavery was legal. The last way that you can think about this is by asking, okay, what's the probability that if I'm going back in time, at least one of my ancestors goes back to either source population, so African or European. And what you see here, so the same x-axis as before, this is per generation. On the y-axis is the probability of seeing an ancestor in that generation. This also peaks again during the height of the transatlantic slave trade, so you see a probability of roughly 96% of finding at least one African or European ancestor during this period of time. And you see, right, that in the beginning, the probabilities are kind of low because we know our fraction of parents are really low. We see it peaks during the transatlantic slave trade and then tapers off again when we have more African American parents than either African or European. So with that, I'll kind of summarize what we've done here, right? So we've taken information that we have about the transatlantic slave trade and demography. We've incorporated it into our model, and with our model, we're actually able to estimate the number of European American ancestors and African ancestors that an African American individual can have. And so it's on the level of hundreds for African individuals and tens for Europeans. So One thing that we want to think about, though, is, what does this mean overall for, U.S. history? I think it's like a truth that we know is quite obvious. And I think it's worthwhile to really explain to people in the context of history the relevance of our work. So that's one of the things that I'm really would like feedback on. If you guys have suggestions for this project and where you think it would be well received, that's something that I think we as computational biologists should always think about is what our work is doing, what the goal of our work is, and how we can best communicate that to the individuals who are interested in this information. So I know this topic is very heavy, but it's something that's really dear to my heart, and I'm still working on. So the future directions are much lighter. So in the future, we're expanding this to K-Way's admixture problem, and this is work that's going to be done with Ellie Armstrong. So we have sets of captive tigers. So she's amazing. She's currently a postdoc with Joanna Mountain, but she somehow convinced a bunch of zoos and Carol Baskin to send her samples. So we have data from a bunch of zoos and some Tiger King data. And our goal is to roughly extend this model to K-Ways. And then here what I'm showing is, so this is a wild tiger genome, and then 3 samples of tigers that are captives. We want to infer the number of ancestors that are going from, so there's all the wild tiger populations up there. How many ancestors for the captive population can trace back to each lineage? So thankfully, for at least the zoo, they keep a really great pedigree. We have a bunch of trio data, so we can roughly make a demographic history that's just as detailed as what we had before. So this is the next bit of work that's well on its way. And with that, I think I made time for some questions, but I also want to thank the Rosenberg Lab, who I never took a picture with because I did a COVID postdoc. And thank you for your time and for listening.